continuous random variables, and the normal distribution. Now, as part of the discussion today, I'm going to show you a couple of other continuous distribution types. I am not going to hold you responsible for those. I'm simply showing them to you so you can kind of see how continuous distributions look like in a context that's not only the normal distribution. But for this course, most of our time with continuous distributions is going to be spent on the normal one. The normal one is what I really need you to be able to work with. Okay? All right. So I'm going to start by talking actually about the standardization process. You may have seen this before if you've done any kind of statistical class before. You may have done z-scores, and that's what this is about. We'll talk about how to compute a z-score and how to interpret what it means. It's very useful for comparing things that are of different types. If you're talking about comparing apples and oranges, for instance, you can actually do that with z-scores. Makes it nice and simple. Then we'll talk about what it means to look at a continuous random variable or continuous distribution, which might model a continuous random variable. And finally, our third part of the discussion today will focus on the normal distribution, which I said is the key example of a continuous random variable that we plan to work with. It turns out we'll be working with it in the next 3 modules, 6, 7, and 8. Well, I guess in 8 we'll be dealing with, well, we'll see. 6, 7, and 8 will focus primarily on the normal distribution and one other continuous distribution called the t-distribution, which we'll see when we need it. All right. So I think I've answered questions that you had from the previous discussions or homeworks. If there are others, you're welcome to ask now. Oh, yes, sure.
So I tried to go back and rewatch the lecture from last time because I had trouble with my using my daughter's iPad.
Sure.
And it didn't seem like it was going to let me unless I did the embedded quiz. Is that normal, or do I just skip past the quiz?
You should be able to. I tried to set it so that you could do that.
Okay.
Especially for those of you who are here, you've already met your attendance requirements, so the quiz is not required.
Okay. And the printout for this week's lecture notes, I didn't see that in the pull down.
I'm not sure I know what you mean by that.
The PowerPoints you're using right now?
Yes.
I previously printed up all the other ones, and I was just had been trying to print this up ahead of time.
Oh, I'm sorry. I don't usually post them ahead of time. Actually, I was still working on them about 30 minutes ago. So.
Okay, good. I thought
I updated
lack of sleep.
And I've been trying to add a few things that make it clearer visually what's happening. I know that statistics can be really complicated with all the symbols floating around. And the more pictures I can show you that make it clear what's happening, the easier it'll be to follow. So I'm constantly updating that, and the drawback of that is, of course, I don't have them ready to post until after the discussion. I will put them up after our class is done today, though, so they'll be right there at that point.
Okay, thank you.
Good thing. All right, good question there. Are there other questions? All right. So, Sherry, if you had a chance at some point, see if you can use a different machine to watch that video. And if it's still doing the same thing to you, send me an email, because then I need to track down what's happening. Perhaps the setting is broken somewhere, but I'm hopeful it's just a one-off with whatever machine you're using at one time. All right. So, as I said, the standardization process allows us to compare things that would normally not be easy to compare. And so one of my favorite examples is a sports argument. You know, it really is more about which sport do you prefer. But I'm an NBA person. The Golden State Warriors in 2015 and 2016 were just an amazing team. And they still have a number of that core together. They won 73 games, which broke the Chicago Bulls record from, I believe it was 1998, was it? Or 96, I can't recall anymore. Anyway, 72 games is what they won, and that was, at the time, thought to be unbreakable. It was kind of amazing. They lost 3 games, I think, in the last month. So they were on track for a far better result, but they still did quite well, and I think they won 16 games and lost 1 in the postseason that year, something like that. It was a crazy good year. Well, Warriors won 73 games in 2015-2016, and little asterisk, they actually did not win the championship that year. Interesting results, how that goes. That was a very impressive accomplishment. Right? It had not been done before, and who knows, it may be a long time before we see that again. The Seattle Mariners had an amazing accomplishment in Major League Baseball. They won 116 games in a 162-game season in the year 2001. That's really impressive as well. Now, the win percentage there is not quite as high, but there's much more of a randomness element, I guess you would say, in Major League Baseball. The averages, the season win percentages tend to be much closer to 50%, simply because it's a lot more games and they're decided by a fewer number of runs. So it's very easy for outcomes to swing one way or the other in individual games. Which one of those things is more impressive? Well, again, you could say that it depends on your favorite sport, but we could actually ask the question, and we could think about it in the context of how hard it is to win that many games in each sport. That's what standardization allows us to do. We can decide which accomplishment is more impressive by comparing them to their peers. All right, another example. Suppose you have one person who's an athlete and run a 4-minute mile. That's a really impressive accomplishment. There are people who can do that, quite a few in fact, but it's still a pretty rare accomplishment. There are also people who scored an 800 on the SAT math, which is again a rare and impressive accomplishment. Which one is more impressive? Again, does it depend on your interest in sports, athletics, versus academics? It doesn't have to be any of those things. We can actually compare them to other runners and to other test takers and use that information then to standardize and decide which one is actually a more unusual accomplishment. And again, that's what standardization will do for us. It allows us to ask those kinds of questions in ways that might not seem approachable at first, but because of the standardization process, we actually have a way to compare them. So how do we do it? Well, as I said before, we do it with z-scores. And so I'm going to give you one version of the formula, and there are other versions as well, but they all come down to an observed value minus an expected value over some equivalent of the standard deviation. That is a mantra you'll hear from me a lot over the next few modules because we'll be using it in different contexts, sometimes with individual values and means, sometimes with proportions, sometimes with even other things. But in each case, observed minus expected over whatever the standard deviation equivalent is what we'll be using. Okay, so in this particular example, since I'm calling them a z-score, I'm setting z equal to a single data value minus the average data value in my set, in my sample, divided by the standard deviation in my sample. Okay, so this is a sample z-score. I could do the same thing with a population mean and a population standard deviation, if I have those.
Could you say that again?
So this formula is taking the individual data value I'm comparing. I'm computing a z-score for one particular y value. And what I do is I figure out how far is that one y value from the average. And I divide that difference, that deviation from the average, by the standard deviation. For this particular example, I'm using a y bar, which comes from a sample, and s, which is the sample standard deviation. If I had a population value, I could compare it to the population by subtracting the population mean and dividing by the population standard deviation. That'd be a mu here and a sigma here. The idea is still the same. It's observed minus expected over the standard deviation. Okay. So for instance, if I'm looking at the NBA situation for the Golden State Warriors, the observed number of wins was 73 out of the 82 games. Okay. Now, think about this for a second, but since every game has one winner and one loser, the average number of wins across the 82-game seasons has to be 41. So I know immediately I'm taking 73 minus 41 and dividing by whatever the standard deviation happens to be. Now that would have to be calculated, so I just used a simple number here so we can see what it would look like. If the standard deviation is 10, that's pretty close to what it would be on average. Then my z-score would be 3.2. So what that 3.2 means is that the Golden State Warriors were performed 3.2 standard deviations better than the average. When you get a z-score, it tells you how many standard deviations above or below the average that your value was. So a score of 3.2 means I was 3.2 standard deviations above the mean. A score of -2 means that I was 2 standard deviations below the mean. This scaling allows us then to decide which event is more unusual. So if I have the Golden State Warriors with a z-score of 3.2 and the Seattle Mariners with a z-score of 3.6, then the Seattle Mariners actually did a little bit more. They were a more unusual accomplishment. Okay. I don't actually know. I didn't do the calculation for that, and of course I would need the exact standard deviation to do this, but that's the process. Okay. So questions about this formula? I'm going to talk to you about what this does to the distribution of the values that you have. Okay? Those of you who've taken an algebra class before, you may have seen transformations of functions. We're going to be talking a little bit about things related to that here with transformations of data. Okay? So we'll think about what that actually does to the big picture. All right. So the first thing I'm doing is I'm taking my observed value and subtracting the mean from it. Now, if I do that for every value that I observe, what does that do?
Changes it to a different mean?
Yeah. Does anyone know what mean it changes it to?
A lower one?
Yeah, well, if the mean was positive, yes. If the mean was negative, it actually makes it a higher one. So what it actually does is it moves the mean so that it's at 0. It shifts everything, left or right, whatever needs to be done, so that the average is moved to 0. But the scale is exactly the same. So all I'm doing is taking all my data points, however they're spread out, and shifting them so that they end up at 0. Okay? So that's the effect of the shift. And what that does is it affects all the measures of position by adding or subtracting the same number to each one. It's whatever the mean happens to be. Okay? So again, the average moves to 0, the mean moves to 0. But other measures of the center, things like percentile, and measures of position like minimum and maximum, or quartiles, those things will all be moved by the same amount. So I'm literally just, it's a translation if you're thinking of transformations. Now, what does it do to the measures of spread, like standard deviation, IQR, and range? Well, if I take everything and I move it by the same amount, the amount it's spread out by doesn't change at all. I'm taking the entire structure and just moving the whole thing. So the scale of it, the width of it, the distance between quartiles, those things don't change at all. It's simply the location of everything that changes. So it changes the position, doesn't change spread. Okay. That's just the first part of the formula. That's the part here in the numerator, where I subtract the mean. Now the other part is after I've done that, I divide by the standard deviation. So what does that do? What that's going to do is it's going to stretch or shrink my collection of data. I moved it so that the average, the middle part, middle part is 0. And when I divide by the standard deviation, I'm either going to shrink it or stretch it out, depending on which scale it's on, so that the standard deviation moves to 1. If my standard deviation was 10, then that scaling factor divides by 10, and now I have a spread where the standard deviation is 1. Okay. So what does that do as a net effect? It affects all of the values, both position and spread. And what it does is it multiplies or divides them all by the same constant. Okay. And do be careful, if I've already done this shifting first, it multiplies the shifted amount by that constant. All right. So the key takeaway is when I subtract or add a number to a set of data values, I change position measures like the mean, the median, the mode, the quartiles, but I don't change the spread at all. When I divide or multiply by a number, which this division by the standard deviation does, then I'm changing the spread and the position. So I'm changing all of those measures, including IQR and standard deviation and variance and range. So let's summarize what this does, because this will be important when we look at the normal distribution. When we standardize using z-scores, it doesn't change the shape of the distribution. It shifts things and changes the scale, but the overall picture is the same. If I were to zoom in on that scale, it would look exactly the same as it was before, or zoom out, depending on what happened before. But in either case, it would look the same. It's simply been moved and either zoomed in on or zoomed out on. Okay. So the shape is not changed. It does change the mean. It moves the mean so that it's now at 0. And it does change the spread. It changes the spread so that now the standard deviation is 1. Okay? And so when we're doing a standardization, it makes our lives easy because we know exactly where the mean is. We know exactly how much the standard deviation is. And so when we look at a specific value like x equals 2, I don't have to do anything else with it. I know it's 2 standard deviations away. And I can compare that directly to somewhere else where I've computed x equals 2.1, and I know that the 2.1 is further away from the mean. Simply because I know 2.1 is a bigger number than 2. And that's all I need. So this standardization doesn't change the shape, moves the center to 0, so that the mean is now 0, and changes the spread so that the standard deviation is now 1. Those are the key things to remember. We will do some examples of that, but I think now is a good time to take a short break before we jump into continuous random variables. Are there any questions about what we've talked about so far? Just computing z-scores right now. We will do some examples at the end of the discussion. In that case, on my clock, it's 9:40, so let's take a 5-minute break, and we'll return at 9.